Hey there. Ever wonder how a network of computers or sensors can collectively figure out the right answer without a central leader? Like, how do they all agree on something without anyone in charge? That's where gossip algorithms come in. Think of them as the digital version of neighbors chatting over a fence. But here's the twist. What if some of those neighbors are lying or sending corrupted data? How do the others still get the right picture? Today, we're diving into two groundbreaking algorithms, GORANK and GOTRIM, that solve this exact problem. They're like the ultimate team players for decentralized networks, ensuring reliability even when some nodes are unreliable. Let's break it down. Imagine a group of friends trying to guess the price of a car. Most say $30,000, but one secretly shouts $1 million to mess with the group. If they just average everyone's answers, the result would be way off. That's the problem with traditional systems. They're vulnerable to bad data. But what if the group could ignore that one loud voice? That's exactly what GOTRIM does. GOTRIM works like a classroom where students pass notes. Instead of sharing their exact answers, they swap hints about whether their number is high or low. Over time, the class figures out the real average without getting thrown off by the one kid trying to sabotage the game. It's all about filtering out the noise, like tuning out a loudspeaker in a crowded room to hear the actual conversation. Now here's the magic. GORANK and GOTRIM don't need a central boss. They're fully decentralized, meaning every node, like a sensor or computer, talks only to its neighbors. It's like a game of telephone where everyone passes a message to the person next to them, and eventually, the whole network agrees on the same answer. But how do they know they're right? The researchers proved these algorithms converge, which means they get closer to the correct answer over time. Think of it like a snowball rolling downhill. The longer it rolls, the bigger and more accurate it becomes. For GORANK, the speed depends on how connected the network is. If everyone's friends with everyone else, it's like a party where everyone talks at once. If it's a sparse network like a small town, it's slower but still works. Here's where it gets technical. The algorithms rely on variance, a measure of how much numbers fluctuate. If everyone's guesses are close, low variance, the system stabilizes quickly. But if some nodes send wild outliers, high variance, the network adapts. GOTRIM uses a technique called robust averaging, where nodes discard extreme values before sharing data. This is mathematically proven to shrink variance over time, even in messy, real-world networks. In tests, GOTRIM outperformed old methods by a mile. When data was corrupted, it quickly zeroed in on the real average, while others got stuck following fake numbers. And GORANK. It's like a super-efficient rumor mill. It figures out rankings faster than ever before, even in networks with unreliable connections. This isn't just cool math, it's the future of smart systems. From self-driving cars to climate sensors, these algorithms keep things reliable even when things go wrong. Next time you see a network of devices working in harmony, remember, behind the scenes, GORANK and GOTRIM are quietly making sure the system doesn't crash. So what do you think? Are you ready to dive deeper into the math that powers tomorrow's technology? Let me know in the comments, because the next big breakthrough is just a conversation away. Thanks for watching. If you want to explore the papers behind GORANK and GOTRIM, hit that description box. And don't forget to like, subscribe, and join me next time when we unravel the secrets of quantum machine learning. See you then.